Welcome to this explainer. Today, we're doing something really exciting. We're using live, unsimulated data to actually map out a massive physical anomaly at the very edge of the Milky Way. It's a set of hard, empirical measurements that absolutely challenges everything those standard textbooks tell us about dark matter and the whole structure of our galaxy. So let's just jump right into the data together and see how this entirely reshapes our visual picture of the cosmos.
We're going to start with a pretty glaring contrast, 2,953 on one side and a tiny little 47 on the other. That is a massive stellar traffic jam that honestly simply shouldn't exist under our standard astrophysical models. What we're dealing with here is a shocking, totally lopsided cosmic reality when it comes to how stars are distributed at the extreme edges of the Milky Way. So, you might be wondering, what is really happening out there at the edge of the galaxy? Well, conventional science kind of assumes our galaxy is wrapped in this neat dark matter halo. They picture it as this diffuse, perfectly symmetrical sphere of invisible mass and old orbiting stars. And hey, if gravity is the only major force to play here, the visual edge of our galaxy should look incredibly neat, tidy, and basically identical in all directions. But, spoiler alert, the actual shape of our galaxy's edge paints a very different picture. To really test this assumption, we aren't relying on simulations. Simulations are often built on the exact same ideas we're trying to test in the first place. Instead, an independent coder literally bypassed the middleman. They use Python to pull live, raw celestial coordinates directly from the European Space Agency's Gaia DR3 registry. We are talking about an unfiltered, direct handshake with the database so we can see exactly where these stars are physically located. Now, to make sure our visual data is absolutely pristine, they had to set up some pretty strict physical filters. They isolated distant outer halo stars and deliberately excluded the noisy, thick galactic plane that sits closer than 20 kiloparsecs. They also required valid radio velocity measurements and just dropped any negative parallax errors entirely. Basically, we're carving away all that cosmic static so we can look exclusively at the precise boundary layer of the galaxy. And wow, when we look forward along the galaxy's path of motion, the data revealed something stunning. The distribution of matter didn't just smoothly fade away into the void like some gentle gradient. Instead, it hit a sudden, hard truncation wall at exactly 99.42 kiloparsecs. The stars literally just stopped. It's a sharp, unmistakable visual cliff right there in the data. Which naturally leads us to ask, does this wall exist in all directions? I mean, if this boundary is shaped by a central, invisible gravitational well, like a standard dark matter halo, that wall should look identical no matter which way we look, right? The sphere should be totally uniform. So if we expand our spatial volume and look behind the galaxy, do we see that exact same wall? Well, no. When the wide field query dynamically split the sky into two opposite hemispheres, that neat symmetrical illusion completely shattered. Over 98% of those boundary stars, 2,953 of them to be exact, were just jammed onto the forward leading edge. Meanwhile, the trailing hemisphere was practically empty, registering a measly 47 stars. If we expand the distance window even further, we can really see this massive forward squeeze zone stretching a dense wall out to nearly 200 kiloparsecs. Just compare that steep visual drop-off to the trailing void, which barely registers anything and cuts off way earlier at roughly 150 kiloparsecs. We are absolutely forced to interpret a wildly lopsided visual reality here, with almost the entire outer population packed so tightly into just one sector. It suggests we aren't looking at a static, symmetrical cloud at all. The data confirms we're actually looking at the geometry of a fluid cavity slamming into intense directional resistance. This visually stunning asymmetry forces a massive paradigm shift. It completely replaces the neat, uniform sphere of the dark matter assumption with a dynamic, physical, fluid interface. It's modeled exactly like our own solar system's heliosphere, complete with a compressed front and a totally evacuated trailing wake. To really wrap our heads around this, let's talk about ram pressure. Think of a ship plowing through the ocean and creating that churning bow shock. It's the exact same concept. As our galaxy moves, it slams into the intergalactic medium. This generates a massive, high-pressure bow shock on the forward front. The galaxy is literally pushing against the universe, and the universe is pushing right back. And this brings us to a really beautiful piece of physics called Jeans instability. This is the critical threshold where gas density and pressure become so intensely squeezed that they trigger immediate gravitational collapse, sparking the birth of new stars. Normally, this process takes eons, but a massive external shock wave, that can force it to happen almost instantly.
So, let's break down how this reaction actually builds. First, the galactic core pushes gas outward. Second, that outflow slams violently into the intergalactic ram pressure. Third, this massive squeeze mechanically compresses the gas way past that Jeans instability threshold we just talked about. And finally, boom, instant pressure-induced star formation right along that leading wall. This entirely answers the mystery of why almost 3,000 stars are bunched up on that one specific side of the galaxy.
On the flip side, the trailing hemisphere acts as an expansion wake. As the galaxy moves away from this space, the gas diffuses and relaxes. Without that intense mechanical compression, it never achieves the pressure needed to trigger star formation. As a result, we get exactly what the Gaia data visualizes for us, a dark, quiet void containing only 47 stray stars. But wait, if this active fluid mechanism perfectly maps the location, birth, and confinement of these outer stars, it creates a pretty fascinating theoretical collision with standard textbook physics. Because remember, the textbooks rely entirely on dark matter to keep these high-velocity boundaries from flying apart. So where on Earth does dark matter actually fit into a fluid galaxy? Comparing these two models side by side reveals a really stark contrast. Where dark matter theory relies on invisible mass and this symmetrical geometry based on standard orbital mechanics, the fluid model goes a completely different route. It relies on measurable external ram pressure, a highly lopsided wake, and the Euler fluid equations. The most intriguing takeaway here is that instead of relying on a hypothetical, undiscovered invisible mass, the Euler equation allows us to explore stellar confinement through a massive, measurable external pressure gradient. It offers a well-understood physical fluid dynamic that perfectly maps to the lopsided visual reality we are literally observing right now in the sky. Under this incredibly visually driven lens, the outer galaxy is not some dark matter tomb. We are completely redefining the stellar halo. It is a turbulent, highly energetic fluid boundary interface. It features an active high-pressure stagnation wall, and its entire geometry is dictated entirely by cosmic resistance. Think about it. These thousands of stars aren't just randomly drifting relics of ancient mergers. Under this fluid model, they are active, glowing tracers born directly from a frontline wall. This completely frames dark matter effects as the physical consequence of high-pressure fluid environments, rather than some undiscovered mystery particle. By tossing out the simulations and replacing theoretical assumptions with live, completely asymmetric spatial data, we are left staring at a fundamentally different shape of the universe. It really makes you wonder, was the dark matter we've been endlessly searching for simply the physical, fluid mechanics of the cosmos, pushing back, hiding in plain sight all along? Definitely something to think about the next time you look up at the night sky. Thanks so much for joining me on this explainer.